Hello dear students, welcome to Functional Studies 101. If you are new to this YouTube channel, kindly hit the subscribe button and don't forget to turn on the notification bell so that whenever new contents are made available, you will not be left out. We continue with our presentation on the mock exam that was given to the students of the Leipzig University. That's University of Leipzig in Germany. This paper is titled Analysis 1. Okay, and this is problem 4, which is a function analysis. We're asked to analyze this function. Whenever you're asked to analyze a function, there are things you need to consider, which I will disclose in the course of this video. So make sure you watch, follow, and don't forget to subscribe. Without wasting much of your time, let's get started. So whenever we are asked to analyze a function, it is the same thing like telling you to study that function right from its domain to its graph. Okay, so our function is given as f of x equals to what you see there. F of x is equals to x squared times the natural log of x. So from this function, we know that this function is defined. This first part of the function is a polynomial, while this one is what? A logarithmic function. This natural log of x is what will define the domain of this function. This function will be defined only when x is what? Strictly greater than 0, because natural log of x is defined only for values of x strictly greater than 0. When it is equals to 0, the graph turns to negative infinity. I know you are familiar with the graph of natural log of x. So in this case, our function f of x is defined only when x is strictly greater than 0. From here on, it means our domain of definition will be x such that x belongs to the interval. In interval notation, you can write it like this, as a set of values. Okay, x belonging to this real number belonging to this interval. So from here, after you've evaluated the domain of definition, because that's where everything will be focused, we now have to evaluate the limits at the bounds of the domain. What's the limit as x tends to positive infinity? The boundaries, we have positive infinity, 0 from the right. Okay, 0 from the right, x is greater than 0. It means we have to evaluate the limit as it tends to 0 from the right. So the limit as x tends to infinity of f of x, as x tends to infinity, natural log of x grows, while x squared even gets even more larger, so the product will get more larger, so it tends to what? Infinity. What about the limit as it tends to 0 from the right? When the f of s, as x tends to 0 from the right, thus we are moving closer to 0, f of x would approach 0. Let me explain why. This function is not defined as x equals 0 normally, which would have posed that this graph should have a vertical asymptote. But this factor cancels that effect. Let's analyze and see. As x tends to 0 from the right, this natural log of x grows to negative infinity. It becomes, when they say 0 from the right, take a value greater than 0, but not very far from 0. Okay, so you can take 0.00001 and evaluate natural log of that. It will become what? A negatively large value. So as x tends to 0 from the right, f of x will approach what? This natural log of x will approach a negatively large value. But this part of the function, when x is very small, remember when you square a very small number, it becomes very, very small. So when you multiply a very, very small number by a very large number, that answer is approximately 0. Yes. So f of x will tend to what? So as x tends to positive 0 from the right, this guy goes to negative infinity, but that growth is counteracted by what? This x squared, which pulls the value back to 0. Slightly negative, but almost 0. That's why we say a limit as x tends to 0 from the right of f of x is approaching 0. It is not exactly 0, it is approaching 0. Okay, hope you understand that. So now we know very well that f of 0 is not defined because according to domain of definition, it is defined only for values of x strictly greater than 0. At 0, the function is not totally defined, so there is a hole at the origin. So now f of 1 is equals to what? 0. By observation, without thinking much, we know that the natural log of 1 is 0, right? The logarithm to any base of 1 is 0. So it means that this whole function as f of 1 will be what? 0. Everything will become 0. What we are doing here is looking for the intercept. There is no intercept, it does not touch the origin. That's what it means here. This graph does not touch the origin. Okay, it doesn't touch the origin. We will see that into play. As we have replaced, this is now the y-intercept. The value of y, the value of x that will make this this function to be 0 is called the x-intercept. So the only intercept to our graph is the point 1, 0, the point with abscissa x equals to 1. This is where the graph cuts the x-axis. So after doing this, we have to examine the derivative. To differentiate this function, this is a product of two functions, a polynomial and a logarithmic function. So I'll keep the first term unchanged. That's we're applying the product rule of differentiation. Keep the first term unchanged, differentiate the second term. Where you differentiate natural log of x, you know it's 1 over x. So I have x squared times 1 over x plus, you now keep natural log of x unchanged. The second function is differentiate the first. So differentiating x squared is 2x times natural log of x. So when you simplify this one will just give x squared divided by x is x. So we have x plus 2x natural log of x. From here, you can factor out the x. So I have 2 natural log of x plus 1. From this stage, we have to examine whether the graph has stationary points. F prime of s is equals to 0 implies 2. Remember, x is not equals to 0. The function is not defined as 0. So the only part that can make f prime of x to be equals to 0 is 2 natural log of x plus 1. So that's why we write that. And from here, we have natural log of x to be minus a half, giving us x to be what? E exponential to negative half, 1/2. From this step, it is clear we have to evaluate what? The function value at e raised to the power minus half, so that we know whether the value that will be either a maximum or a minimum. We will do that by a test. So from this step, f of negative 1 on 2, exponential of negative 1 on 2, when you replace, this is my function, I replace anywhere I see x, I replace it by exponential of negative 1 on 2. When you square this term, remember it's raised to the power 1 on 2. So when you raise it, when you square it, the 2's cancel out, leaving out e raised to the power minus 1. And e raised to the power minus 1 is 1 over e. 1 over e. Then natural log of x in this dimension, natural log of x is minus 1 on 2. So we have minus half times 1 on e. So that's minus 1 on 2e. From this stage, we have that what? The only point, the only turning point, a stationary point on this our graph is this point. Okay, this thing is the same as what? 1 over e raised to the power a half, and e raised to the power a half is square root of e. So if you wish to leave it like this or you write it like this, it's the same thing. So this is a stationary point. As a recap, when you are analyzing a function, always start from the domain of definition. The limits are the bounds. Evaluate the intercepts if you wish. It's very important. You will need it while sketching the graph. You have to evaluate the derivative, the derived function, find the stationary point as we have done. Let's move on. So after getting the stationary points, we now have to look for whether there are points of inflection, and that can be done only when you evaluate the second derivative. The second derivative of this function, I'll apply the product rule again. I'll keep this first function, these 2 natural log of x plus 1 unchanged. I differentiate x is 1. Product rule, because the product of 2 functions. Then now you keep this x unchanged, you differentiate this. Where you differentiate this, you have 2 divided by x, okay, this part now. And then differentiate the constant is 0, so you have 2 divided by x times this x will give us 2. From there, at the end of the day, we end up with f prime double prime of x to be equal to 2 natural log of x plus 3. From this step, we have to evaluate at the point of inflection, f prime prime is equal to 0. If an f prime prime can only be 0 only when this part is equal to 0. This function now is equal to 0. From there, we have natural log of x to be equal to negative 3 and 2. From here, we have e raised to the power minus 2 on 3 to be our x. When you solve, you raise both sides to the power e and simplify. So f of this value again will be equal to what? Negative 2 3 on 2 exponential of 3. That's I come to my function, anywhere I see x, I replace it by this value and simplify the result. And a smart way of doing it is just to know that for this case, natural log of x in this case is minus 3 on 2, and when I square this term, this thing will go. We'll be left with e raised to the power minus 3, which will now go to 1 over e to the power 3 times this value, and you have the result. Hope you are understanding. If you don't understand anything, make sure you comment so that I can explain to you one-on-one. So in point form, we are saying that the value of this function when x is e raised to the power minus 3 on 2 is equal to this value. So in point form, you write it like this. So this is the point of inflection, and we are going to show it. So we are going to use the second derivative test to know if this is our stationary point, because after determining the stationary points and point of inflection, right, after determining those points, you have to know whether the stationary point that you got was a maximum point or a minimum, a local minimum, or a saddle point. Let's look at it. When f prime prime of that value, that x value at that point is greater than 0, we know that it is what? A local minimum. When it is less than 0, it's a local maximum. And when it's equal to 0, you cannot conclude. You have to go back to the first derivative test. So according to this first derivative test, when you evaluate f double prime, this is my f prime prime. When you evaluate f double prime of e raised to the power minus 1 on 2, you end up with 2. And 2 is greater than 0. So it means that the point B, this point, is a local minimum. Okay, it's a minimum turning point. So after doing all of this now, we have to draw our variation table to summarize all what we have done. So our variation table will look like this. We have values of x there. Then the sign of the gradient and the behavior of f will now be here. So when you're writing the variation table, always start from the lower bound of your domain, the lower bound. Our x was strictly greater than 0, so my lower bound is 0. We write 0 there. And then there was a turning point at 1 divided by square root of e, and also there was positive infinity at the other bound. Make sure you put all the turning points there, because we want to know how the graph is changing shape, how it's varying in different intervals, whether it's increasing or decreasing. That's the main purpose of a variation table. So we know that at this point the f prime prime is 0 at this point, at the point when x was equals to 1 divided by square root of e. It was a turning point. So in this interval the function is negative. When you test, take a value between 0 and 1 over e, square root of e. You test in the gradient function, the answer will be negative. In the other interval, it is positive when you test. And also, the function, as we know, it is decreasing. It means it will be coming down like this towards the stationary point. So what's the value at the stationary point? We had the y value is negative 1 on 2e. Since we know that we have used the second derivative test and we know that that point is a local minimum, so this is what the minimum point. So the graph will fall down to that point, then rise back. So in that case, what is the value? As x was tending to 0 from the right, it was 0, right? So we put 0 there. And then the value as it was tending to infinity, it was positive infinity, you put it up there because it is rising to that point. You cannot put it down here. Why here you cannot put it down? Because it is what? It is not rising up, it is falling. Okay, so the graph is falling from 0 to this point, then rises back to infinity. This is our variation table. From this table now, we can now draw our graph. Our graph will look like this. I don't want to waste time in drawing, so just look at the picture of the graph. I will show you how you can. This is how you sketch from your variation table. It's a sketch. Just draw your axis. Okay. I know that for my argument of this point, the graph does not touch the origin. The graph does not touch the origin. Let me zoom it out for you so that you can see something. No, just keep it like that. The graph does not touch the origin. When you draw your axis, right, you know that the graph passes through x equals to 1. This is an intercept. Plot all the intercepts that you have. There was a point of inflection, you indicate it, and then there is a minimum turning point. At this point, this is 1. At this point, 1 over what? Square root of e. This is the x value. Then now locate the y value, plot the point. Plot the point of, in this interval, there was a point of inflection. So you plot it. So it means that the function was decreasing. When it reaches that point, it continued to decrease. It's a saddle point. Okay. So from this point, between this x value here like this to this side, the function was decreasing. That's why it's coming down. After that, it take a turn, a U-turn. It now increase now to what? Passing through the intercept. Are you seeing that? And then increase to positive infinity. This is just a sketch. You can expand the axis, like draw it, like stretch it like this, so that your graph will have a better shape. Okay, let me just zoom it out so that you can better see. This is what I'm saying. You can see the graph does not touch the origin. It is not defined at x equals 0. So when x was tending to 0 from the right, when they say 0 from the right, it means we are moving from here, coming towards 0. The graph was almost 0, but it was still negative. It was something that was a negative value, which was, it can be negative 0.0001 million zeros and then 1. You understand now? So it is not actually touching, it is just almost. There is a hole here, that's why we indicate with that circle. It is undefined at that point. There is a hole there, we put a circle there. So this is the graph of our function. When you're asked to analyze a function, that's what you're supposed to do. And we have come to the end of the presentation. So I would like to thank you all for your kind attention. Hope you enjoy it. Please, if you don't understand any step, don't forget to hit me up in the comment section and I will reply to you. I'm not perfect, okay? I'm not perfect. If you find that I said something that was not supposed to be said, feel free to comment me. Comments critics and corrections are accepted, okay, because that is just for the betterment of everything I'm doing here. So keep the comment section hot and enjoy the video. As you watch it, if you don't understand, re-watch it again. When you finish watching, don't forget to share. Like this video, share, subscribe, and don't forget to turn on the notification bell. See you in the next presentation. This is Temgo 48 signing off. Bye. I love you all.